Hi everyone. Today we're going to study continuity. A function f of x is continuous at the point x equals c if and only if it meets the following three conditions. Condition 1, f of c exists. Condition 2, the limit of the function f of x as x approaches c exists. We need to check whether the right-hand limit is equal to the left-hand limit, and the common value is L. And this value L is the same value of the limit of f of x as x approaches c. Condition 3, the limit of f of x as x approaches c must be equal to f of c. Let us see this example 1. Consider the following graph and answer the questions. Our function is y equals f of x, and the function is represented by this graph. We can see here that the graph is defined when x is from -1 up to +3. And here is the graph. Take note that when x is equal to 1, there is a point that corresponds to that. The first question is, does f of 1 exist? The answer is yes. And f of 1 is equal to 1, as described by the point. Question B, does the limit f of x as x approaches 1 exist? In this case, let us examine the one-sided limits. Let us begin with the right-hand limit, and we write limit of f of x as x approaches 1 from the right, denoted by that positive power. Observing the graph, when x is approaching 1, the graph is also coming close to a y value which is 2. So the answer here is 2. Considering now the left-hand limit, and we write here the limit of f of x as x approaches 1 from the left, denoted by that negative power. Observing the graph here, when x is coming to 1 from the left side, the graph is also coming close to a y value which is 2. So the answer here is 2. We can see here that the right-hand limit is equal to the left-hand limit. So the answer for letter B is yes. And we write the limit of f of x as x approaches 1 equals 2. That is the same value of the one-sided limits. Question C. Does the limit of f of x as x approaches 1 equals f of 1? The answer is no. We can see here that the f of 1 is equal to 1, while the limit of f of x as x approaches 1 is equal to 2. Question D. Is f continuous at x equals 1? The answer is no. Question E. To what new value should f of 1 be changed to remove discontinuity? The new value of f of 1 must be equal to the limit of f of x as x approaches 1, and that is 2. So we write here 2 as the answer. Question F. Is f defined at x equals 2? The answer here is no. We can see here that there is a gap when x equals 2. Question G, is f continuous at x equals 2? The answer is no. Question H, what value should be assigned to f of 2 to make the function continuous at x equals 2? Observing our graph here, we can see that when x approaches 2 from both sides, the graph is coming to a y value, and that is 0. So we write here 0. These are the answers for example 1. Let's see this example 2. Say whether the function graph is continuous on the closed interval -1, 3 or not. If not, give a reason. This is graph A, and the function is y equals f of x, and the graph is here. Observing the graph, we can say that the graph is not continuous on the interval because there is a gap or hole when x equals 2. This is graph B. Our function is y equals h of x. This is our graph. And we can see that the graph is continuous on the interval. This is the graph C. Our function is y equals k of x. And here is the graph. Observing this graph, we can conclude that the graph is not continuous on the given interval because there are two discontinuous graphs for the function. Technically, we can write that the limit of k of x as x approaches 1 does not exist. Considering the one-sided limits, we start with the right-hand limit. The limit of k of x as x approaches 1 from the right is equal to 0. While the left-hand limit, and that is the limit of k of x as x approaches 1 from the left, is equal to 1.5. Since the one-sided limits are not equal, so the limit itself of the function as x approaches 1 does not exist. Moreover, the full graph cannot be manually drawn without lifting a pen. This is our final answer. Today we're going to study piecewise continuous functions. Let us define piecewise continuous functions. A function is piecewise continuous on an interval if it has a finite number of subintervals on which the function is continuous. Let us see this example. Check if the function f of x is continuous at x equals 2. In here, the function is a piecewise function, and we have two functions here on the given subintervals. The first function is for x minus 2 over x minus 1 when x is less than or equal to 2. The other function is 4x minus 2 when x is greater than 2. Remember about the rule of continuity. The equation must satisfy the three conditions. Number 1, f of c must exist. Condition 2, the limit of f of x as x approaches c exists. And condition 3, the limit of the function must be equal to the f of c. In this problem, the value c is the number 2, so we substitute it here. So we say now that in the condition 1, f of 2 must exist in the function. Number 2, the limit of f of x as x approaches 2 must exist. Condition 3, the limit of the function as x approaches 2 is equal to f of 2. Let us first check if condition 1 is satisfied. For our f of 2, we're going to use the function 4x minus 2 over x minus 1. We are using this function because of the equality on the symbol here, and that corresponds to the f of 2. Evaluating this fraction now, when x is equal to 2, we have 4 times 2 minus 2 all over 2 minus 1. Simplifying the numerator, 4 times 2 is 8 minus 2 becomes 6. In the denominator, 2 minus 1 is 1. And 6 over 1 is simply 6. So f of 2 is equal to 6. So we say now that condition 1 is satisfied and the value is 6. Let us check condition 2. The limit of f of x as x approaches 2 must exist. In here, since we have a piecewise function, let us check first for a right-hand limit. The limit of f of x as x approaches 2 from the right. In this case, this greater than symbol denotes the right side function. So we're going to use the function here, and let us substitute this function in our notation here. So we have the limit of 4x minus 2 as x approaches 2 from the right. Evaluating this limit, it means we will substitute the number 2 for the x. So 4 times 2 is 8, and minus 2 will give us 6. Let us check for the left side limit. That is the limit of f of x as x approaches 2 from the left. In here, this less than idea in the first subinterval denotes the left side function. So we're going to use this function for our limit here. So we write now the limit of 4x minus 2 over x minus 1 as x approaches 2 from the left. Evaluating this limit, we substitute the number 2 to every x in the function. So we have 4 times 2 minus 2 all over 2 minus 1. So we have 6 in the numerator over 1 in the denominator. We simplify this into 6. We see here now that the right-hand limit is equal to the left-hand limit and the value is 6. So we say now that condition 2 is also existing. So the limit of f of x as x approaches 2 is equal to that same value, which is 6. Now for condition 3, we will check if the limit of the function as x approaches 2 is equal to f of 2. Our limit is equal to 6 and f of 2 is equal to 6. So condition 3 is satisfied. So we say here, since the three conditions are satisfied, the function is continuous at x equals 2. This is our final answer. Let us see example 2. For what values of a, the function f of x is continuous at x equals 1. We have two functions here for the respective intervals. The first function is ax minus 1 when x is less than or equal to 1. The other function is 3x squared plus 1 when x is greater than 1. For our solution, since f of x is continuous at x equals 1, we assume that the limit of the function f of x as x approaches 1 is equal to f of 1. Also, the limit of f of x as x approaches 1 from the right is equal to the limit of f of x as x approaches 1 from the left. Substituting the corresponding functions, we have now the limit of 3x squared plus 1 as x approaches 1 from the right is equal to the limit of ax minus 1 as x approaches 1 from the left. Let us substitute the values of 1 to the respective x. So we have 3 times 1 squared plus 1 equals a times 1 minus 1. Simplifying this equation, we have now 3 plus 1 equals a minus 1. The left side becomes 4. If we transpose the negative 1 to the left side, it becomes 4 plus 1, and that is equal to 5. So the value of a equals 5. This is our final answer. There is a note here that says the polynomial function and rational function are continuous at every point in their domains. Example 3. Determine whether the function f of x equals x squared minus 9 all over x minus 3 is continuous at x equals 3. Justify your conclusion. Note that the function f of x here is a rational function. Now let us write the three conditions. In order for this function to be continuous at x equals 3, first condition is f of 3 must be defined. Second condition, limit of the function f of x as x approaches 3 must exist. Number 3, the limit of the function f of x as x approaches 3 must be equal to f of 3. Let's begin with the condition 1. Let us evaluate f of 3. This is our function. So we have 3 squared minus 9 all over 3 minus 3. Simplifying, we have 9 minus 9 all over 0, and then 9 minus 9 is 0 over 0. We can see that 0 is in the denominator. We say that division by 0 is not allowed. Also, 0 over 0 is what we call an indeterminate form. Now we say f of 3 is undefined. So, for condition 1, f of 3 is not defined. Therefore, we will stop here. We will not proceed to steps 2 and 3 anymore. Directly, we can conclude that f of x is not continuous at x equals 3. Example 4. For what values of x is f of x equals x plus 1 all over x minus 4 continuous? Note that f of x is a rational function, so it is continuous except when the denominator equals 0. We're going to copy this denominator down here, and we're going to get the value of x where this denominator should not be equal to 0. So, x minus 4 should not be equal to 0. Then we solve for x. The negative 4 we transpose to the right, so it becomes x is not equal to 4. For our conclusion, we say that f of x is continuous in all values of x, except when x equals 4.